Welcome to the 16th lecture for Physics 4B. In this and the next lecture, we cover a little bit of circuit analysis we can cover with the amount of physics we have learned so far. Again, depending on your approach, you may be looking at this lecture immediately after lecture 15, which introduced electric current and Ohm's law, or you may be returning to this material after having studied magnetism first. Either approach should be fine for the sequencing of topics. So, we start this lecture with Kirchhoff's rules, which are not telling you any law of physics that you don't already know, if you really think about it. But what Kirchhoff's rules tell you are the things to focus on when you are analyzing circuits. So, we show examples of applications of Kirchhoff's rules in the remainder of the lecture. We use Kirchhoff's rules to derive the resistor addition formulas that you may already know. And as we get into more general application of Kirchhoff's rules, where we encounter situations involving resistors that cannot be added as a series or parallel, we make our definitions of series and parallel precise, so that we don't accidentally add resistors that we shouldn't. And we wrap up with an example of how we can model batteries in circuits more realistically. That's it for this lecture. We will cover more examples, both easier and harder, of applications of Kirchhoff's rules in the next lecture as part of our coverage of DC circuit analysis. Yeah, so this is the Ohm's law is what we covered last time, and this should be in the back of your mind for everything you do. Because when you're dealing with the circuits, this is what really circuit comes down to. Let me sketch, I don't know, a complicated looking circuit, or let me save a little bit of time. Instead of sketching a circuit, let me use one of the problems that's posted here as an example of a circuit that you will soon be able to analyze. The example I like best is this one, because it's simple and yet complicated. So, we won't work this out right now, but I'll just use this as an example. So let's say this is a circuit you are given. By the way, is everyone familiar with the circuit symbols? I don't think we actually talked about it in class, so let me write it down. This is not something we covered in class last time, but let me tell you some of the circuit symbols so that I can use the shorthand that's in the diagram and it'll make sense to everyone. So these are the circuit symbols. So right now on that diagram you see three different kinds of symbols. Here's the first one, symbol that looks like straight line. What do you think that symbol represents? No, not the arrow, just the straight line.
Negative.
No, just the lines in the, these lines. That's part of a circuit symbol. It's a standard symbol. When you see those lines, all that means is wires. So we didn't cover this properly. We didn't explicitly cover this in class, but so you know what wires are, right? Conducting material. What do you think some of the properties that you should attribute to these wires is? Like what kind of property would you associate with wires? In a way, it's different from these other symbols you see. Any guesses? Yeah? Constant voltage throughout the whole wire, right? Okay, so why do you say that?
Because it's a conductor, so just between
Yeah.
two resistors.
Yeah, it's a conductor, and really, this is an important part. Chris said between two resistors. So when you compare the resistance over this wire, you compare the resistance over this wire to this resistance, whatever small resistance in wire there might be, it's compared to this, it's so small that we are going to approximate it as being zero. Now, you saw in class last time that it wasn't zero. When I had a long piece of wire, it had a resistance of like 1 or 2 ohms.
But for the purpose of circuit analysis, we are going to assume that wires have zero resistance. And as a result of us assuming that wires have zero resistance, it's going to have same voltage throughout. So whatever parts are connected by a wire, you can say that it has the same voltage. You guys are kind of using that already. So I guess that's the most common and important symbol. The other two symbols are the squiggly line. It represents a resistor. Oh, I don't have any resistors out here. Let me bring out some resistors so that you can see what they look like in case you haven't seen it before. So what I'm passing out are, well, take one, pass the rest. Take one, pass the rest. I'm going to want it back though. Take one, pass the rest. These are what we call resistors. This is 1 kilo ohm resistor. And when you think about resistor, this is the typical resistor I want you to think about. As in, it has a value of 1 kilo ohm, 1000 ohm. That is the typical value of resistance. 1 ohm is actually too small, like a wire has 1 ohm. Sometimes you will see bigger resistors or smaller ones. This is a low power resistor, as in this is rated for 1/4 of a watt. And when this dissipates more than 1/4 of a watt, it actually will burn out. So the resistors that are rated for higher power will be bigger so that it can dissipate more energy without burning out. So whenever you see this squiggly line in your circuit diagram, what this represents are resistors. So it will be characterized by some resistance R. And this R can actually range a lot. It can be as small as a few ohms, and it can be as large as a giga ohm. But I want you to be in the mindset of a typical value is around 1000 ohm or 1 kilo ohm. That's the typical value of resistance. Sometimes, in homework problems, you will see an author talk about a resistor having 1 ohm, 2 ohm. Just chuckle a little bit and then move on. 1 ohm and 2 ohm are not reasonable values of resistance. So this is the symbol for resistor. And I guess this one, property of this is pretty simple. It's an element that has this resistance, which obeys this Ohm's law. The last symbol is this symbol consisting of 2 lines of unequal length. This is important that the lengths are unequal. One is longer and one is shorter. Any ideas what this symbol represents?
Power supply, or
Power supply, I like to call it battery because this particular symbol is meant for voltage sources. In fact, a DC constant voltage source. If we can change the voltage, there will be some different symbol. So this is what we would call battery. And the longer end, that's supposed to be the positive end. It's the higher voltage end. And the lower end is the negative end or the lower voltage end. And the property of battery is that it's an ideal battery would provide some constant voltage. So the voltage difference from the low end to the high end, this voltage difference is supposed to be whatever voltage of the battery given. So it provides voltage difference of some whatever voltage of the battery is. That's the property of battery. So that's it. Those are the circuit elements. So what's represented here? It's a circuit that you can imagine building, right? Now that you know what each of these elements represent. You have 2 batteries here, somehow separated. And you have 3 resistors this way. And you can imagine, connecting this battery to this end with a wire, and take another wire, connect it to resistor here, and make all these other connections with however many wires you need. So when we have a circuit like this, then I want to first describe what we mean when we say solve a circuit. Because it's like, Anybody here into, I don't know, game theory or computer science, artificial intelligence? Like, what does it mean when people say tic-tac-toe is a solved game? Like, tic-tac-toe is actually solved game. Like, what does that mean?
Finding the best possible answer for the manner of winning it.
Yeah. So in other words, given the rules of the game, tic-tac-toe is a very simple game. You know exactly what the best moves are in every situation. On the other hand, chess and Go, they are not a solved game. As in, computers can be programmed to play it, but it's just yeah. So here, I want to describe what it means to solve a circuit. So when you are given a circuit, some of the parameters will be given. Like in a board game, like a tic-tac-toe and chess, some of the things will be given to you. The rules of the game are given to you. So here, what I want to say is, well, when you have the circuit, you might be given this. So usually the typical values that will be given to you will be the voltages that will be given. This will be given. Because when you're building a circuit, you know what battery you are using. So some voltages will be given. And typically, the resistances will be given. Because this marking on the resistor, there's supposed to be rules on reading it so that you can figure out what resistance this is. Or I usually measure it. I don't bother reading it. So these resistances will usually be given. And description of the setup that gives all these values will have completely determined this setup. And what it means to solve this circuit is for us to figure out, well, what other things are there in the circuit for us to know about, might be interested in. So, for example, we might be interested in how long these batteries are going to last. And if we want to know that, we'll have to figure out how quickly the energy is draining from these batteries. Or we might want to know how much these are heating up. Or so there's going to be one particular parameter that we are going to want to know to answer any other questions we might have about this circuit. What is that one physical observable or something that we can measure that we would want to be able to figure out from this setup? There's one very particular type of quantity that we would, a type of quantity that we would like to know. Yeah, current. So having determined all the voltages, actually maybe not all the voltages, so I know the voltage difference here and here, but I don't know the voltage here, right? Okay, all right. But having determined all the resistances, it turns out current is the one information that if we have about this circuit, that any other questions we have about the circuit, we can answer it. So here, in this circuit, there are actually, there can be 3 different currents. One is already labeled there. And actually, I think if you read the problem, this is the given, but whatever. So here's one current. Let me label this I1. And there's going to be another set of current that's flowing through this branch. Let me label that I2. And there might be another set of current that's flowing through this branch here. Let me label that I3. So this is how I want to describe solving a circuit. When you have solved a circuit, you will know all these parameters. So that now when someone asks any question about power dissipation or what is the voltage here, at that point it's now a single step process to just answer that based on your knowledge of the voltages and currents of this circuit. Yeah. So it's a very general problem solving approach. That's why I'm trying to talk in general terms. And what we are going to do now is introduce tools for doing exactly that. Introduce tools for if you are given all the voltages and resistances, tools for figuring out the current. Or it can be the other way around. In this question, it's actually voltage and this current that's given, and you're supposed to figure out these other things. And it's like, I want you to be reminded of the standard strategy in physics 4A. So in physics 4a, it didn't almost matter what kind of problem you're dealing with. If we dealt with the forces, then you started out with this set of steps. So it's very similar approach we are taking to circuits. It doesn't matter what kind of circuit it is. If it's a circuit problem, this exact same set of steps that we are going through will help you come up with a set of equations which you can then solve to completely determine everything to know about this. Okay? So the tool that we are going to use, it's a set of two rules. It's called, so I just found out in the during the summer break that I've been misspelling this name forever. There are two H's, and I've been also mispronouncing the name probably forever. I've been saying Kirchhoff, but I think it's supposed to be, it's a German name. I think it's supposed to be Kirchhoff. Is that right? Whatever. I'll try to say it right, Kirchhoff, or it's a German name. I don't have to pronounce it right. However you pronounce this name, so I usually say Kirchhoff, but I don't think that's right. Kirchhoff. Whatever. Kirchhoff's rules. So these rules are the beginning point for solving any circuit. And it's almost like Newton's laws of circuit. So let me write down this. But I want you to realize that when I have described the I'll just say Kirchhoff. That's what I'm calling. But I know it's I'll just Kirchhoff. When I have given you Kirchhoff's rules, you will feel like that I haven't told you anything new. That's the feeling I want you to have. So let me state Kirchhoff's rules. And so Kirchhoff's rules, two H's, there are two rules. And I think usually people state the loop rule first, but I like to state the junction rule first for a reason that I'll explain. So this is what junction rule says. So it's a rule regarding junctions. What do we mean by junction? Well, it's kind of what it sounds like. This is a junction, right? Like interstate junction. This is another junction. And to tell you the truth, actually, I can treat this as a junction too. But this becomes a trivial junction, you'll see when you see the rule. So this rule involves junctions, and it involves a current involved with this junction. So what junction rule says is, let's say you have, I'm just going to draw a part of a circuit. Let's say you have a part of a circuit where several wires meet at this point. And maybe there's some current coming in, and there are several different currents going out. And what junction rule says is, well, add up all these currents. Add up all the currents that you labeled as coming in. Add up all the currents you labeled as going out. Then when you add up all those currents coming in is equal to current going out. Do you agree that this should be true? Right? You would have guessed this, right? If I just asked you. Like what would be the relationship between the currents coming in and going out? Right? This doesn't surprise anyone. The current coming in. Why is this true? Yeah, conservation of charge. And we talked about how it's really hard to accumulate charges anywhere. So yeah, so this is true. And so the value of Kirchhoff's rules is that it highlights the very basic facts about circuits that you'll be using. It's not telling you anything you don't already know. But what it's telling you is that these are important facts for you to utilize in solving a circuit. Let me give you the loop rule. So loop rule tells you this. So it involves loop, as the name says. And I guess, let me ask you this question, just so that to help you start thinking about what loops are. How many loops do you see here? In this one circuit, how many loops do you see? Okay, I hear 2. Okay, let me go. How many people see only one loop? Okay, how many people see only two loops? Okay, how many people see up to 3 loops? Okay, how many people see 4 loops or more? Anyone see 4 loops or more? No one see 4 loops or more? All right, let me draw the 3 loops that some of you are thinking. Yeah, there's at least 3 loops here. 3 sort of independent, 3 loops. So there's 1 loop here. So, you imagine going in a loop. Like imagine this is like a road. And you start at one point, you take a little journey, go around, see if you can come back to the same point that you started. That's 1 loop. And you can do the same thing here. Start here, go around, and come back to the same point. That's another loop. And the other 3rd loop that some of you are realizing is I can, let's say, start here, and I can go around the entire circuit and then come back to the same point. That's another loop. That's not like the other 2 loops. To tell you the truth, I think there should be an unlimited number of loops. Not that it's useful, but let me draw one other loop that, this is if you're trying to be difficult. But if you're trying to be difficult, you could call this a loop. Let's see. I could start off from here, go around this path, go down this way, come down here, and refuse to end here, keep going, and then go around here, and then come back here. That's a loop. I'm not saying that you should define loops that way. So here, the maximum number of useful loops is 3. So, with the loops, what I want to start you to thinking in terms of is really the only thing that's required in a loop is that you're starting and ending at the same point. There's not, other than, you can jump around in the circuit. Other than those 2 things, there's nothing really restricting how you define your loops. So, when we talk about loop rule in Kirchhoff's rules, I'm just going to mess up my Kirchhoff's rules. So that's So it's that kind of loop that it's referring to. So let's just be difficult. And let's say we are talking about the orange loop that I drew, not any of the other saner loops that's here. So I want to be able to make some kind of statement about these loops that I have drawn. I'm just going to erase the current marks because that's easier. So let's say, we are going with the craziest loop I've drawn, the orange one. And I want to say something about it. And I think one thing I can say something about, as I imagine going around this crazy loop, is I can think about voltage change. So, it's a circuit. Whenever you're dealing with a circuit, there's always going to be only 3 things you're interested in: voltage, resistance, and current. In fact, actually, 2 things: voltage and current. And resistance happens to be one of the ways voltage and current can be related. But as we start introducing other circuit elements like capacitor, actually you have seen capacitor, you will realize there's really 2 things that you are always interested in the circuit: voltage and current. And it's a question of how do you relate those 2. So as I think about this loop, all right, current sounds complicated. So I'm going to say, okay, I'm going to focus on the voltage. So as I start at this point, this is my starting point on the loop. What I can look at is, all right, what are my changes in voltage? How much does the voltage change as I go across this element? Everyone agrees voltage should change as I go across the battery? Okay. How much does the voltage change as I go across this resistor? How much does the voltage change as I go across here? How much does voltage change as I go across here? And so on. Skip over here. And then how much does the voltage change as I go across here? And then back across here, and then across here. So I'm going to imagine I add up all the changes of voltage as I go around the loop. What value do you think this should be? 0. Why 0? It's the correct answer. It's the correct intuition, but I want you to be able to justify it.
The voltage out is the difference between voltage is the same.
Sorry, I didn't catch the first half. Voltage.
So voltage out from the
There's no quite. It's not voltage out. I guess this is the intuition I want you to have. So voltage, as we talked about, relates to potential energy, right? What's the one parameter that potential energy depends on? There's one dynamic quantity that all potential energies depend on. Gravitational potential energy, electrical potential energy, position, yeah. Potential energy is energy of position. So when I had this thing going through this loop, it's the gravitational analog of that would be me saying, all right, I take this mass and I'm going to take it on loops. Sometimes I'll move sideways, sometimes it'll move up and then down, and then some complicated path, completes a loop, comes back to the same point where it was. And I ask you, what is the total change in the potential energy of this mass? And you say 0, like Crystal says. Why is it 0? It's at the same position. So, when you add up all those complicated changes, well, as long as you come back to the same point, all those changes are guaranteed to add up to 0. But sometimes, people say potential energy is path independent or all that stuff. So all of that comes down to say, when you add up all those changes over a loop, it must add up to 0. Right? So this is something else that you already kind of knew. So I'm going through this long discussion to make sure that it makes intuitive sense. But the short version is that it should make intuitive sense. I'm not telling you anything new here. And so these are the two rules that we use for solving any circuit. So the rest of the class today will be that demonstration. I'm going to use these two rules, the fact that these are true, and Ohm's law from time to time, to derive some of the formulas that you might already know. How many people here know how to add resistors? In series. How many people here know how to add them in parallel? Some of you. So I haven't given you those formulas yet. I'm actually just going to derive it in the class today using these two rules. I'm going to use these two rules, the fact that these are true, and Ohm's law from time to time, to derive some of the formulas that you might already know. How many people here know how to add resistors? In series. How many people here know how to add them in parallel? Some of you. So I haven't given you those formulas yet. I'm actually just going to derive it in the class today using these two rules. So let's do that. So let me draw the two circuits for doing exactly that. So the first circuit that we'll look at using Kirchhoff, never mind, I'm just not going to say the name. Kirchhoff's rules is, so resistors in series. This is actually the easier one. It kind of looks like this. So I can have a battery here. I'm trying to draw it small so that I can use the rest of the space. Battery here, resistor here, another resistor right after that, and then comes back to the battery. So this is a circuit. There's a path for current to flow. There's a path for current to flow like this. And let's say that this battery has some voltage V0. And the resistances of these resistors are some values R1 and R2. And here's a question that someone could ask. The question that It's a term that you will see in your textbook also. There's a phrase, equivalent resistance. Or if you are looking at really fancy textbook, I don't think that one's ours. They might even say Thevenin equivalent resistance. Which is, there's some theorem proven by the guy named Thevenin who proved that something. But comes down to, what does the phrase equivalent resistance of these two resistors, any ideas what that might refer to? Like equivalent in what sense? Because if I have two resistors, it's how much resistance there is in the way they are arranged in the circuit. So it's a black box view that I want you to think about. So imagine that these two resistors are put inside the box. So they are like literally inside the box, black box, and you have no way of looking directly inside the box. All you can do is you might be able to apply voltage, and you might be able to measure the current that's going in. So if you have this black box imagined, then this is the quote-unquote equivalent circuit you can imagine building. As in, you have a battery here, and inside this black box, instead of imagining some complicated arrangement with two resistors, you imagine that maybe it's just a single resistor that's in there, that it's only one resistor in there. And what you see outside with the same voltage that somehow produces the same amount of current, it'll be consistent with the resistance of this resistor here being what we are going to call equivalent resistance. So that's the sense in which this is the equivalent resistance. Does that make sense? Yes? No? I feel like I'm going through a long way to explain something that is actually simple. In fact, here, if I asked you what is the equivalent resistance, what would you have said? Any guesses for the formula? R1 plus R2, you just added them, right? And that actually turns out to be the correct answer. So when it's in series, it's actually pretty simple. But we'll go through this rule to prove that that's the case. Where it gets more interesting is when they are in parallel. So let me draw the picture here first, and then we'll go through the mathematics for both of them together. So when resistors are in parallel, then this is what it looks like. So I will draw them parallel, but we'll talk about that a little bit later. So I have two resistors in parallel lines hooked up to the same battery. But being in parallel lines actually is not what parallel means. We'll go through the actual definition of parallel in circuit. So we are applying some voltage V naught, which results in some amount of current out of this battery. And these two resistances are some values R1 and R2. And someone could ask the same question again. What is the equivalent resistance? What do you think, just taking a guess, what do you think equivalent resistance of these two resistors added together should be? Here, should the equivalent resistance also be R1 plus R2? Like, you know it's not. You have seen it in your circuits introduction lab that when you build the circuits this way versus this way with your two light bulbs, they actually do behave differently. And this circuit is different from this. Let's see if we can use the definition, apply the definition we used here in a consistent way. So I'm going to define equivalent resistance in this sense. These two resistors, I'm going to once again imagine that they are in a black box. That I'm going to put a box around them. And the only access I have to these two resistors is some input lead and output lead. two set of leads to one set of two leads to apply voltage difference with. That's all the access I have. So I imagine building, looking at the circuit with this black box here. I'm applying the same procedure I applied to that other circuit. And what I can say is, all right, this black box has two leads going into it, and I can apply some voltage to those two leads using a battery. And when I do that, I measure some current going in. And inside the box, this is what I'm going to imagine. Instead of there being some complicated arrangement of two resistors, either this or that, I'm going to say maybe it's there's only one resistor in there. And based on what I see, I try to deduce what is that resistance. And whatever this resistance is, that is the equivalent resistance. Yep. So the formulas that you might know about adding resistors, it's formulas for trying to figure out what is the equivalent resistance in these two limited circumstances. And some of you might know the formulas already, but let's derive it. One more preliminary matter to take care of before we actually do that. So I told you before that to solve a circuit means to figure out all the currents in all the different branches of the circuit. Because I was claiming that once you know that, then you can answer any other question that people ask you. I didn't say to solve a circuit means to figure out equivalent resistances. Because sometimes there is no such thing as equivalent resistance. So here, if what I said was true, then I should be able to figure out, I'm going to figure out what the current is. From knowing the current, I should be able to figure out equivalent resistance. What do you think that final connection is? Once I figure out the current, how would I use that to figure out equivalent resistance? Okay, so I know the current and voltage. How does that relate to the equivalent resistance? Yeah, you relate it through Ohm's law. So whatever the single resistor there is, it must be consistent with this expression, that equivalent resistance is equal to whatever voltage I applied divided by the current that's passing through. Good? And in fact, it will be the same formula here. Whatever that equivalent resistance is, well, it must be consistent with voltage applied over the current. If that's not, then this model of the black box I have is just completely wrong. And the theorem that Thevenin proved is that, I think what he proved is that as long as your circuit consists only of resistors, then no matter how complicated this is, that you can reduce it down to this. There's one more part to that theorem, but we'll go into that later. So we are going to try to find out current, and once we do that, we'll put it in here, and we'll try to express this equivalent resistance in terms of these resistances alone. So let's do the simple one first. Do you see any junctions here? No junctions, right? Okay, so that means as I try to apply Kirchhoff's rules, I can forget about applying the junction rule because there's no junction to use it on, and I'll just use the loop rule. Right? So what I'm going to say is when I go through this circuit in a loop, all the changes of voltage must add up to 0. All right, that seems simple enough. So I need to define the loop first. I mean, there's only one loop, but let me just be careful in saying what that loop looks like. Let me start from this point here. It looks like a good starting point. And starting from here, I'm going to go across the battery, keep going, go across the resistor, across the second resistor, and then come back, return to the same point. So let me write that down. Let me write down the loop rule with all those changes of voltage. So loop rule says that change of voltage added up all around the loop. Well, as I go across the battery, what's my change in voltage? So plus V naught or minus V naught? Does the voltage go up or go down as I go across this battery? Up, right? I'm going from negative to positive terminal. So it's a plus, oops, V naught. All right, I had to keep going. Now, as I go across this resistor, so I know it's going to be given by Ohm's law, but the question I'm asking would be, is it up or down? Down. The voltage will drop as you go over a resistor. Yeah, because the electrons, the charges would lose energy, and it comes, yeah, okay. So minus the current, there's a symbol I assigned to it, so I'll use that. Minus current times the resistance. And for the second resistor, it would be the same thing, except with the resistance of the second resistor. So minus IR2. And then I come back to the same point. So the loop rule says that this must add up to 0. So this is your system of one equation that you're trying to solve for. How many unknowns do you have? 2. Wait, what are you counting as unknowns? Is V not unknown? No. Is I unknown? I current? It is unknown, right? I don't know the current. It's not given. Oh, I see. You guys are treating the resistances as unknown? Resistances has to be given. Right? Otherwise, yeah. So you have to assume that resistances are given. Yeah. Yeah. So yeah, if both resistances were not given, then there would be no way to solve this. You can go from here to here, but there's no way to go way backward. So here, the only unknown is the current. The current is unknown. And this is what I mean. Usually, the situation is that voltage and the resistances are specified. Because in a real physical situation, that's usually the case. So, one unknown, one equation, I can solve it. Let me solve it for current I. It's not that. Let me skip all the algebra steps, and let me have you stare at it for a while and tell me if it looks reasonable. Does this sound right? Okay, yeah. So to do that, what you would have to do is move this to the other side, factor out I, so you get R1 plus R2, divide it out, then you get this. Okay, so now that I have the current, I can use this formula here. According to the formula that we guessed before we did all of this, the equivalent resistance is equal to the voltage divided by the current, V naught divided by R1 plus R2. Well, the voltages cancel, and you end up with, it's 1 over this. So let me just flip it back around, R1 plus R2. This is what you would have guessed. And this is, that's what you would have guessed. And that's what applying Kirchhoff's rule says. Good? Yeah, so maybe this is not all that impressive. Like, we just took the long way to get something that you already knew. So let's do this one. Unless you've been reading ahead in the textbook, or you might not know what the formula is. There's actually a way to kind of guess at it. The one way to guess at the formula would be to use this relationship that we covered in Monday's class, that the resistance can be related to the resistivity by length over area of the conducting thing. And you could use this to try to guess at it, but I want to spend most of our time in the circuits. So let me use the circuit problem solving tools, Kirchhoff's rules, to figure out what the equivalent resistance here is. Here, do you see any junctions? How many junctions do you see?
2.
You see 2 junctions, all right. So let me label them. And by the way, all I'm saying now is summarized in the handout that you see, but I want to give you some intuition for the advice I'm giving you in that handout. So I have 2 junctions. All right, so I think I'm going to be using junction rule then, right? So I need to add up all the currents coming into a junction, add up all the currents going out of a junction, set them equal to each other. That would be one equation I get. And junction rule applies to each junction. So there's a junction rule that applies to this, and there's a junction rule that applies to this. So before I can write down my junction rules, anything I should do first? Yeah, I'm kind of hinting at it, but I need to label my current. So here, this current was the one same current throughout the entire circuit. Yes? Right? Here, can you say this current is the one same current throughout the entire circuit? No, once you come across this junction, you face a choice. The current could go up or to the right, which means it splits off. There's going to be a current that goes here and current that goes here. So let me label them I1 and I2. And I guess I'll keep using the same symbol I. Good. And once you enter each branch, and within the branch, it's the same current until it meets another junction. And within this branch, it's the same current until it meets another junction. Good. All right, so that's the first thing we had to do. We had to label the currents in each of the branches so that we can actually write down this equation. Let me write down junction rule. And since I see two junctions, let me use both of them. So let me label the junctions as junction 1 and junction 2. Let me write down the junction rule equation for 1. So I add up all the currents coming in. What are the currents coming in? Just the I, and it's the way I have it labeled. So I is equal to the currents going out, I1 and I2. I1 plus I2. All right, so that's one equation. Let me get myself another equation here. So equation 2. By the way, how many unknowns do you see right now? Really, only 2? 3. What are those 3 unknowns? Yeah, they're all unknowns. I have unknowns in terms of other unknowns. So I'm looking for at least 3 equations, which is why I'm looking for as many equations as possible. And in fact, this is the area where portable TA and I differ. Portable TA will tell you, using these 2 rules, come up with as many equations as possible. I don't tell you that. I tell you the exactly correct number of equations. Not one more, not one less. And this is really why. So let's say I'm going for as many equations as possible. So I'm going to use all my junctions. So I used the junction 1. Let me use junction 2. Okay, what are my currents coming in? Yeah, I1 plus I2. What are my currents going out? Yeah, the I is the current that's coming out here. Hey, haven't I seen this equation before? Yeah. So if you include both of these equations into your system, you have created a dependent system of equations. Meaning solving a dependent system of equation gets way more complicated than solving an independent system of equation. So the advice I'm giving you in circuit solving, that's also in the handout, is geared towards avoiding dependency. So I'm going to do what I need to do to avoid introducing the second equation, which doesn't actually add anything. So this is the advice that I give you in the handout. When you see the number of junctions in your circuit, the number of times you should use the junction rule is the total number minus 1. Leave 1 junction unused. So that's what you see here. When you have 2 junctions, the very last junction you use is guaranteed to give you an equation that's already dependent on your system of equation. So here it's easy to see they are the exact same equation. When you have more junctions, sometimes it won't look like any of the other equations, but it will be dependent in some other way. So that's why I want you to use the junction rule first. It's the easiest one to say, all right, if I have 2 junctions, I can use only one of those. If there's 3 junctions, I can use only 2 of those. So you know exactly how many times you used to use it.
Is it dependent on which junction you use, or it doesn't matter?
Doesn't really matter. Yeah. I mean, I could have used this junction and kept this and got rid of this one.
Cases like 3 and 4 junctions.
Yeah. So as long as you leave 1 unused, you will be guaranteed to have an independent system of equations. Independent, but not enough. I only have one equation. I need two more, at least two more. So where do you think I can get those two other equations? Yeah, the loop rule. This is the rule that I haven't used. So here's the benefit of having used the junction rule first. How many times do you think I should use the loop rule? Two. And I need to use it exactly twice. I want 3 equations. I don't want 4. I don't want 2. So I need 3 total equations. So now once I have used the junction rule, I have the benefit of knowing, okay, I need to use the loop rule exactly this number of times. So I'm going to try to find the 2 loops here. And let me do, 2. So the general advice I would give is pick the loops in a way they overlap with each other as little as possible. As in, you would not do this. So you wouldn't say, okay, I pick this loop, call that loop 1. And I'm sure no one here will say, okay, having picked this as my first loop, for my second loop, I'm going to pick the exact same loop. Like, would anyone here do that? No, right? You know not to do that. And what I would tell you is when the situation gets more complicated, the equivalent version of it is that you want to avoid overlaps as much as possible. The loops will always overlap a little bit. Let me pick this as the loop 1, and for loop 2, let me pick it this one. So starting from this point, going around this way. So these 2 loops overlap a little bit. They share the same branch here. Some overlap is fine. They are going to have to overlap. But I guess this is an illustration I could give. If I picked, in addition to having picked loops 1 and 2, if I pick a third loop that goes this way, it's going to give you another dependent equation. Can you see that? Why the third loop would give me a dependent equation? Look at how the third loop overlaps with the first 2. Does it completely overlap with the first 2? Right? So, if I imagine going over this loop, say this is my third loop. For every part of the branch I'm going through, has it already been covered by the other loop? Yeah. So that's the sense. That's what I mean by overlap. And when you have a situation where the branch is being covered by your loop, it has already been covered by another loop already, then this is not going to give you any equation it's going to give you a dependent equation. So the advice I give to you is, define your loops in a way that minimizes overlap. So with these 3 loops, I could have used loops 1 and 2, or 1 and 3, or 2 and 3, just not all 3. Because if I do, that moment is when there's complete overlap. Okay, so let me not use loop 3. I'll use loops 1 and 2. So okay, that's begin to sound promising, right? I wanted exactly 2 equations, and there will be exactly 2 equations that probably will give me exactly what I was looking for. So let me relabel these loops so that I don't confuse my numbering system. Let me label this 2, because it'll be giving me equation 2. And let me label this loop 3, since it'll be giving me equation 3. And let me erase this other junction that I'm no longer using. All right. So my equation 2 comes from this loop. So I'm going to go through the same thing I did here before. I imagine starting from here, and as I go across each element, I figure out, all right, what is the change in the voltage? So for the loop number 2, I'm going to first go over the battery. That's going to give me voltage change of plus V naught. And then I'm going to go across the resistor. And my voltage drops. Yes? Everyone agrees? Okay. Minus I2 R2. And then I come back to the same point. So that should add up to 0. All right. So that seems fine. It didn't introduce any new unknowns. So hopefully the last equation also looks fine. The loop number 3. So I start at this point. As I go across this resistor, does my voltage increase or decrease? So I start at this point here, and I go across this resistor from right to left. How many people say voltage increases? How many say voltage should decrease? So at some point, we will summarize this in a sign convention. But here, I want you to gain the intuition that as you go from here to here, voltage is increasing. In fact, that's the only way you can be consistent with what you say here. Because here, you said going from here to here, voltage was decreasing. So if you are going the other way, it must be increasing. And in the sign convention that we are going to come up with, it will have to do with the direction of path you are going relative to the direction of current. When you are going with the current, then your voltage is decreasing. When you are going against the current, then your voltage is increasing. For the resistor, it's a resistor specific rule. So as I go across this resistor, for loop number 3, it's going to be actually plus I2 R2. And then as you go across here, this time with the current, going across R1, it'll be minus I1 R1 is equal to 0. Okay? I have 3 equations, 3 unknowns. I should be able to solve it. Good. All right, so let's just go through it and do it. So, now that it's 3 equations, I'm not going to do the algebra in my head. I'll go through it step by step. So whenever you do algebra, you should take some time to look at it. Try to sketch out a path that's going to be the quickest. So I stare at this for a while. I see that this has a lot of unknowns. I see these two both deal with only one unknown at a time. So if I solve this each for I1 and I2, and then plug it in here, then I'll get an expression for I that's going to be nice and clean. It'll be an expression for I that's not in terms of any other unknown. Okay? So let me solve these each for each of their unknowns. So that's the easy one. I'm going to do that in my head. I2 is, oh, wait, sorry. I missed this. It's okay, now that I realize it, let me change the step a little bit. I'm going to solve 2 for I2, plug that in here, and then solve the whole thing for I1. Then I'll have I1 to plug in here, and I2 to plug in here. Yeah. So I2, still simple. I2 is equal to V0 over R2. So I plug this in here to get the intermediate expression that V0 over R2, V0 over R2 for I2 here, times R2, oh wait, that's just the V0, minus I1 R1 is equal to 0. So these R2s cancel out. So I get a nice simple expression for I1. I1 is going to be V0 divided by R1. V0 over R1. All right, they all look simple. I probably should have expected it because this is actually a simple circuit. I'm not supposed to get super complicated result. So let's plug this into the equation 1 and get an expression for I. The current I is equal to I1, V0 over R1 plus I2. V0 over R2, or I can factor out V0 and get V0 times 1 over R1 plus 1 over R2. Good? Yeah. So to find the equivalent resistance, I can plug this in here and solve for, plug this in here. But let me actually re-express it in a way that's more convenient because it keeps the expression simpler. So let me say, instead of trying to solve for R equivalent, let me say I want to instead solve for its reciprocal, 1 over R equivalent. Okay, so if I'm doing that, then what I'm writing down here is I over V0. I over V0. this makes it simpler because I'm going to avoid the nested fractions this way. So I is just this, V naught times 1 over R1 plus 1 over R2 divided by V naught. So V naughts cancel. And you get this result, that 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. So that's the formula for adding resistors in parallel. In shorthand, sometimes we say in parallel, resistors add in reciprocals. Yeah, there's one useful. There are things we can talk about here, but this is the formula, and we just derived it. I guess the most important thing to know is this, and you can numerically verify this. This equivalent resistance is guaranteed to be smaller than either of these two resistors. It's always smaller than R1 or R2. Yeah. So you guys saw the application of Kirchhoff's rules in very simple cases. And we even derived these formulas. And the truth is, there are a lot of problems you can solve with these. And I hope it's intuitive for everyone how you would extend this in case you're adding more than 2 resistors. Like if you're adding 3 resistors in series. What do you think the modified version of this formula will be?
Adding them.
Just one more, right? What about modified version of this one if you're adding 3 resistors in parallel?
Adding 1 over R3.
And it's just here, right? In reciprocal again. Yeah. So these are pretty useful formulas that you might use, and there are some homework questions that you can do using only these. What I want to point out is that there will be some questions where you cannot solve it using these alone. In fact, the circuit that you see here is one such example. So let me draw a version of this, or one that looks similar to this on that board over there, and I will try to explain why it's impossible for you to answer this question only by trying to add resistors in series and parallel and simplifying circuit that way. So this is what that circuit looks like. I have a resistor up here, and I'm going to actually give them generic labels, R1, and another resistor here. Let me label this R2, and another resistor here. Let me label this R3. And there are 2 batteries. Let me call this V1. And I'm going to say there's another battery here, V2, and not give you the current. So in this circuit, to solve this circuit would mean to find this current. So there's a current that's flowing through this battery. For my own reasons, I'm going to call that current I3. And there's going to be a current that's flowing through this battery. For my own reasons, again, I'm going to call that I2. And there's going to be a current maybe flowing this way here. Let me call that I1. So to solve this circuit would mean to find what each of these currents are in terms of the voltages and the resistances that are given to you. Good? So I keep telling you that you cannot do this using these formulas alone. Why not? I mean, couldn't I add these resistors R1 and R2, simplify this upper half, and then simplify that with this R3 again, and do it that way? Let's imagine that that's what you're trying to do, even though none of you seem to be willing to do that. Then if that was, R1 and R2, are they in series or parallel? They might appear to be parallel. So I should go over the definition of what it means for 2 resistors to be in series and what it means for them to be in parallel. Because, the language that we are using, it's rooted in what it looks geometrically. But let me give you this picture and have you tell me if this represents resistors in series or parallel. Let's say I have two resistors. They are arranged along parallel lines. But let's say I add it to a battery this way. I have a battery here, and I add it to the battery using these lines, these wires. Wire here connects here, this wire here connects here, and this wire here brings it back down to here. So that, you know, it's like what you're doing in lab, right? So here, yeah, why do you say it's in series?
It's a series because there is no consistent voltage for each resistor being
Yeah, I don't want to define series that way because you are looking at it. I mean, there will be situations where two resistors do not have the same voltage across, and it still won't be in series. So series does not mean, yeah. So I want to define series based on what this is, not what it's not. So how would you define this as a series circuit based on what it is? One path for current to follow. You know, they are in series in the sense. One comes first, and then the other comes. So in fact, that's how we are always going to define series. For two circuit elements to be in series, that means when a current flows through one element, that same current must flow through the other element. Whenever that happens, we call that series. So in that sense, is R1 and R2 in series? Look carefully. Current that's going through R2, must that flow through R1? As in, can you say that I2 must be equal to I1? Look at it carefully. If you are saying I2 is equal to I1, what are you saying about I3? Not equal. If you are saying I2 is equal to I1, what is I3? No, use the junction rule. So, you know, I2, I3, and I1, they all meet together in this junction. This is I2, this is I1, this is I3. So can you say that I2 is equal to I1 without knowing anything more? Why not? Yeah. So because of this junction being here, you cannot say I2 is equal to I1. I mean, there's a path for you to go from here to there, but that's not the question being asked when you are saying if they are in series. When we are saying they are in series, we are not saying that there is a path. We are saying that path is the only path. That's what you see here. This path is the only path. That's what we mean. Current that flows through here must, not can, must flow through the other element. Here, the current through here, it doesn't must flow through R1. It can flow through the other elements also. Or, you know, current that's flowing through R1 could have come from elsewhere beyond here. So in that sense, R1 and R2 are not in series. Okay, so we've satisfied ourselves that they are not in series. And the same thing holds for any other pairs of resistors here. None of them are in series. Let me go over definition of parallel. Because I really want to emphasize this. What parallel does not mean not series. And vice versa. Series does not mean not parallel. So they are mutually exclusive, but they don't cover all possibilities. So once again, the same arrangement here. And if I'm imagining connecting them in parallel, I guess this is how I would do. This is what you did in lab. You connected the battery to one set of resistors, and then you used another set of wires to connect these here. So now you would call this in parallel, right? So give me some definition of why you would not call this parallel. While you're thinking about that, let me draw an alternate version of this circuit. If I have circuit diagram that's drawn like this, would you say that these two resistors are in parallel? In fact, let me ask you a different question. Is this circuit equivalent to this circuit? Right? As in, you can imagine taking this, moving it around, not disconnecting anything. Maybe wires might stretch, but not disconnecting anything. You can imagine moving it around to make them look exactly the same. So it's kind of a question of topology. There's a topology joke saying that if you're a topologist, coffee mugs and donuts look the same to you because donut has a hole in it, and coffee mug, in the handle, there's a hole in it. And the other parts of the shape can be deformed without changing anything. It's the same thing with the circuit. When you deform some part of the circuit, as long as you are not messing up any of the junctions, as long as you are maintaining the same connections you have, you can deform the circuit to your heart's content without changing anything. So these two circuits are the same. So if this is parallel, this must also be parallel. So I want to have some definition of these things being parallel that applies to both of them. So how would you define circuit resistors as parallel or circuit elements as parallel?
Something where, let's say something where current can divide into two.
Well, so in this circuit, you see current dividing into two, right?
Or more.
And I'm going to end up saying this is not in parallel with this. So with the parallel, actually, I want you to pay attention to the voltage. Because it comes down to this. When we look at current, there's just way too many possibilities. So with the series, remember, we nailed down one thing, that when you look at the current, one same current passes through all the elements. I want to have something similar here, and if I try to do it in terms of current, I have no chance of doing that ever. So what other thing remains?
Voltage stays the same throughout its travel through the circuit.
Okay, with the voltage, I want you to be careful in stating things about voltage. Voltage does not move. Current does describe flow. So I want to talk about current through a resistor. Voltage does not move. Voltage is measured at a single point. So now you might do this. You might say, okay, voltage at this point is 0 volts. And you might measure all the other voltages relative to this. So when I say two circuit elements are in parallel, what I'm saying is something about voltages at particular points. So without describing anything as moving, because voltage has nothing to do with the movement, it has to do with the values of voltage at particular points. No paths for you to go through. So you are talking about voltage here. So what would you say about the voltage of these elements? You can look at change in voltage. But I want to be actually more specific than that. So this is how I can describe it in a way that's as simple as possible and true in every single instance you'll see it. Let me define points A, B, C, D. So these are points at the ends of each of these elements. And when I want to say these two are in parallel, this is what I mean. Voltage at point A is equal to voltage at point C. And voltage at point B is equal to voltage at point D. Good? I mean, in this particular case, what Kevin was saying also turns out to be true. If this is true, then the difference would be the same also. But I want to state it this way because when you get into semiconductor circuits, deal with op-amps, there's a very strange way of making things that are parallel that are not actually connected. So when we say some things are parallel, it really means their voltages at the end points are the same. That's the definition of something being parallel. Here, the voltage at this end point is the same because it's the same end point. And voltages at these two end points are the same because they are connected by a wire alone. Okay. So using that definition, R1 and R2, are they in parallel? as in voltages at these two endpoints. Is voltage at this endpoint the same as this? Oh, I guess it is. It's connected by wire. Is voltage at this endpoint same as voltage at that endpoint? Why not? Yeah, because of this battery here. In fact, that's the whole reason I inserted a battery there. If you didn't have this battery, you could have simplified this circuit using these rules. You know, add these two as parallel, then the remaining is a series, add them as series, and you're done. But because of this battery, all of that is ruined. These are not in series because of this junction, and they're also not in parallel because of this battery. So this is a good example of a general circuit that you might have to solve, where your circuit elements are not in series or parallel with any other element. So if all your problem-solving tool was this, something you might have learned in high school physics, then you're kind of stuck here. There's no tool that you can use here that's based on these two. But if you know the very basic circuit solving tools, we can go back to here. Come up with a system of equations, and then solve the system of equations to find I1, I2, and I3. Good? What I want to point out is that there will be some questions where you cannot solve it using these alone. In fact, the circuit that you see here is one such example. So to solve this circuit would mean to find what each of these currents are in terms of the voltages and the resistances that are given to you. So this is a good example of a general circuit that you might have to solve, where your circuit elements are not in series or parallel with any other element. So if all your problem-solving tool was this, something you might have learned in high school physics, then you're kind of stuck here. There's no tool that you can use here that's based on these two. But if you know the very basic circuit solving tools, we can go back to here. Come up with a system of equations, and then solve the system of equations to find I1, I2, and I3. So let's do that. Now that I've convinced you that the methods you might have used in high school physics doesn't work, let's use the one that actually works that we cover in college physics. Actually, technically, this is university physics, but I can imagine this being covered in college physics since it's algebra. All right, so we are going to use Kirchhoff's rules. Which of the two rules do I usually use first? Junction rule or loop rule? Junction rule, for the reasons I was explaining earlier. So how many times can I use my junction rule here? I see two junctions. Can I use it twice? How many times? Yeah, I'm going to be able to use it only once. So let me pick just the one to use. I'll use this one to use. So I'm going to use this junction to write down my junction rule. Okay, before I do that, how many unknowns do you think I'll have that I need to solve for? 3, I mean, that's labeled here, the currents that I labeled, right? That's, by the way, one of the reasons to actually label the current in each of the branches. That'll tell you the number of unknowns before you write down any equation. So I'm going to need 3 equations total. So, all right, I got 1 taken care of. I need 2 more. Where am I going to get those 2? Yeah, I'm going to use loop rule twice to come up with my total of 3 equations. And I guess I can pick the same loop I did last time. Yeah, let me do that. I think there's actually some interesting possibilities here. So the loops I'm going to pick are, well, loop involving this. So starting from this point to here, I'll go around, and come back here. This is going to be my loop number 1. And my loop number 2, let me start from this point to here, just behind the battery, and then go around and come back to this point. my loop number 2. And you, oh, sorry. Let me label them by the equation number that I'm going to be using, 2 and 3. And you might want to verify that they avoid overlap as much as possible. That they do overlap in one branch, but that's it. They each have parts that's not overlapping with the other loops. Yeah? So this is my plan for coming up with 1, 2, 3 equations, which will hopefully allow me to solve for 1, 2, 3 unknowns. Good? Okay, so now that I have the plan, let me write down those equations and see if they satisfy my criteria. So equation 1 is based on the junction. What are my currents coming in? By the way, before I do that, let me ask you this question. So current I1, I'm pretty sure that has to be the direction. Because based on the batteries, like I'm pretty sure voltage here is higher than voltage here, right? So I1 has to flow that way. With the currents I2 and I3, is it like guaranteed to be like this direction? There's a possibility that it might be different, right? You can imagine V2 being very, very small. In that case, I2 would actually flow this way. So I guess this is the question I want to touch on and make sure you guys understand. So should I worry about that? Should I sort of try to figure out what the actual direction of current is before deciding on one? Or can I kind of label one direction and stick with it?
Maybe you can label it and use the signs later to...
Yeah. So with the direction of currents, that's actually going to be true in every single case. I could have labeled I1 going the other way. And as long as I follow a consistent set of rules, if the result I get will be correct. And when my final answer gives me negative current, that'll be my indication that I should flip the actual direction of the current. So here, even though I don't really know actual direction of I2 and I3, I labeled it some way. And I'm going to just assume that this is the correct direction and do the rest of the problem that way. So for junction 1, what's my current coming in? Just the I1, right? Follow it, it comes into the junction. So I1, that's equal to my 2 currents going out, I2 and I3. So I1 is equal to I2 plus I3. All right, that seems like a good start. Equation 2 comes from my first loop. So as I go across my battery, I'm going to gain voltage of plus V1. As I go across this resistor, does my voltage rise or drop? Drop. I'm going with the current, so it drops. So it's minus I3 R3. That's kind of why I labeled it I3, so that the numbers go with the resistor. It's easier to avoid the confusion that way. Sometimes equations for circuit analysis, they can get really complicated. Some of your homework questions are that way. All right, I still have another half of the loop. Okay, then from here, I'm going to go across this resistor. Am I gaining or losing voltage? Okay, it looks like I'm losing voltage, but so that's based on the direction of the current that I labeled, right? What if it's the other way? Is that something for me to worry about? The answer is no. Let me write it down and I'll tell you why. So here, I would say, all right, if the current is actually going this way, I would say I gain the voltage of plus I2 R2, right? Now, suppose I was wrong about the direction of the current, that it actually would have been voltage drop going from here to here. Then what that would mean is my answer to I2 would be negative. So this expression still would represent the voltage drop. So when you're trying to figure out what is the rise and drop of voltage, you worry about what direction of current did you label, not what is the actual direction of current. It's a directional current that you labeled that overrules everything else. Because you're trying to be consistent with the direction that you picked. Okay, my last element before I come back to complete my loop. So as I go across this battery, am I gaining or losing voltage? Right, losing. I'm going from positive terminal to negative terminal. Now, what if my direction of current were to flip? Then should I say I'm actually gaining voltage? Yeah, still losing. So with the batteries, direction of current doesn't matter. It's the direction of your path that matters. So that's actually the sign convention. So the sign convention for resistors say that you lose voltage when you're going with the current, you gain voltage when you're going against current. And the second sign convention is the one for battery. It says you lose voltage when you are going from positive to negative terminal. You gain voltage when you go from negative to positive terminal without regard to current direction. So those are the sign rules. It's fairly intuitive once you understand it. So this should be minus V2. That completes my loop. So this is equal to 0. All right, let me finish loop 3. I'll go through this more quickly. So it'll be across the battery plus V2 from negative to positive. Across the resistor with the current, so minus I2 R2. Across the resistor with the current again, minus I1 R1. Come back to the same point, is equal to 0. All right, these are my 3 equations, 3 unknowns. I should be able to solve it, right? Yeah. So, you know, almost all the circuit problems you deal with will be like equation of a system of 3 equations or more. That's why I say, you know, the algebra is going to be more complicated than what you remember from physics 4a. So you should take time to come up with a plan. Like when you see something like this, I have 3 equations, 3 unknowns. It looks fairly complicated enough that I should have an actual plan before I do anything. I look for 2 things. One thing that I look for is there any equation that's in terms of only one unknown? That's the one that I would want to handle first. And that's actually what we did here. There was an equation in terms of only one unknown. I solved for it, and that was a useful tool for me to have. Now, here, there's nothing like that. Then what I look for, the second thing, is there an unknown that occurs a lot? Like I2 occurs in every single one of the equations. So what I'm going to do is, all right, I want to get rid of I2 as soon as possible. So I'm going to solve one of those 3 equations in terms of I2. To get rid of it, then I'll reduce my system down to a system of 2 equations in terms of only 2 unknowns. Okay? So let me do that. I think what I'm going to do is I'm going to solve the first equation in terms of I2. So solve this for I2. So I2 is equal to I1 minus I3. And I'm going to plug this into both of these to get new system of equations that has only 2 unknowns. So plug it in here. Oops. Here. So this is my new equation 2. It'll be V1 minus I3 is fine, R3. And I'm going to plug it in. Do I want to distribute it? Yeah, let me distribute it as I do it. I'm going to plug it in here. So I get plus I1 R2 minus I3 R2 minus I3 R2 minus V2 is equal to 0. Let me do some simplification in place. I have 2 like terms with the same I3, right? So I'm going to combine these 2. So that would be minus I3, R3 plus R2. Everyone agree? Yes? So let me do that. Let me move this around. So it'll be this plus R2. And then minus I1, minus, I1 R2. Good? I changed this around, okay? Good. All right. All right, so this is one of my equations, the new system of equation. I need to do the same thing for equation 3. So my new equation 3 is going to be V2 minus, all right, I have this I2. I'm going to plug this in and do the substitution on the fly. And in fact, let me plan this out ahead of time. When I plug in I1, that's going to give me a like term with this, right? So I'll have minus I1 R2 minus I1 R1. So I'm going to write it down from the beginning as minus I1 R2 plus R1. Good? So I handled this. Let me handle I3 there. So it's minus I3, so it'll be plus I3 R2 is equal to 0. Good? All right, I have two equations, two unknowns, I1 and I3. So I solve for it. I guess from here the choices are like they're equivalent. You can do kind of one or the other, and they would be equally complex. So let me just do one. I'll do it here. I will solve this for I3 to plug it in here. Question?
For your second equation, shouldn't it be plus I1R2?
Sorry, are you looking at this?
Your second, number 2?
This one?
Yeah, should it be plus I1R2?
Oh, it was plus I2, but this I1 that's coming from, yes, I think you're right. Thank you. Yeah, that's why, yeah, thank you. It should be plus. All right, good that we caught that mistake now. All right. Okay, so I'm gonna solve this for I3. So that means, I guess I can imagine moving this to the other side and divide up by R2 plus R3. So when I do that, this is what I'm going to get. I'm going to get I3 is equal to everything on the left-hand side added, V1 minus V2 plus I1 R2. So V1 minus V2 plus I1 R2 divided by this thing that I took over to the other side. So R2 plus R3. Good? Plug this in here. Then you end up with this equation. I think I'm just going to alternate between purple and black. So this equation will turn into V2 minus I1 R2 plus R1 plus this I3. Complicated. So V1 minus V2 plus I1 R2 divided by R2 plus R3 times R2 is equal to 0. All right, it's just going to look complicated. So let me collect all the like terms. So I think I can collect the like terms in terms of I1 on the other side. When I do that, this is what I get. V2 plus all of this that's left here, plus V1, or let me write it this way. V1 minus V2 multiplied with R2 over this. R2 over R2 plus R3. So those terms I have taken care of. 1, 2, 3. All right. And the other terms, I'm going to move to the other side. So it'll be plus I1 R1 plus R2. And then this will become minus I1 R2 squared over R2 plus R3. Good? I can actually simplify this a little bit, I think. Yes. If I combine the denominators, make them share the same denominator, R2 plus R3, then I have to multiply this by R2 plus R3. Believe it or not, that will actually simplify things a little bit. Let me write it out so that you can see what simplifies. So when I write it out, this is going to be I1 divided by R2 plus R3. So I'm factoring out I1 and R2 plus R3 to the front. And this is the rest of the remaining terms. R1 times R2, R1 times R3, R1 times R3, R2 times R2, so R2 squared plus R2 times R3, R2 times R3 minus R2 squared. So what I'm saying simplifies is these two things cancel. Yep. Yes? So that we can say all of this left-hand side is equal to I1 over R1 plus R3 times all of that. It's actually, in some sense, it's simple. 1, 2, 3, these three terms are all three possible pairs of R1, 2, and 3. So it's easier to remember that way. R1, R2 plus R1, R3 plus R2, R3. And to actually solve for I1, I would have to divide both sides by this, and then that'll be I1. And I guess I'm kind of out of space, so I'm going to leave it there. So with the circuit problems, what you will see is that you guys already know how much I hate plugging in numbers, right? But at some point with the circuit problems like this, I do have to give you numbers, because algebra gets horrendous at some point, just with all these different parameters. But so with this, you can see that I can solve for I1 in terms of everything that's known, right? Yes? Like in this equation, the only unknown is I1. If I have numerical values for everything else, I can solve for I1, which means I can plug that I1 into here to get I3, and I can plug that I1 and I3 into here to get I2. So that's how you solve for all the currents in this circuit. So, so this is an example of a problem that can only be done using the general problem solving technique using Kirchhoff's rules. This is all that you need. The rest is something you are figuring out in the course of working out a particular problem. Yeah. So let me actually pose you with this hypothetical, which is the reason for this simulation being here. Because I'm not going to do this with a real battery. As I keep telling you, it's dangerous. When I do this with a power supply, it doesn't quite work as a demonstration because of all the safety features built into power supply that makes them behave not like a battery. So what is the property of battery in a circuit? Like what is the one thing that battery do? Now, it does provide the power, but you will find that that's not very useful in problem solving. So, the fact that battery is like a power supply, it's useful when you're trying to describe things conceptually, like how you would do it in physics 10. But this is physics 4b. I expect you to actually, analyze a circuit. Okay. So, what is the property of battery in that sense? The one thing that battery does was it provides a voltage. It provides a voltage difference. So imagine you have a battery. Then what this battery does is it provides a voltage difference between one end and the other end. And really, this is the one thing you use about the battery when you're solving a problem about circuit. This fact comes into play when you're applying Kirchhoff's rules. Good? Okay. Let's say I'm doing the thing that I keep telling you not to do during lab. And I do this. I take a piece of, I take a battery and connect it to two terminals, negative and positive, with a piece of wire. In other words, I have shorted the battery. So if I short a battery, question is, what happens? And when you look at this circuit, it's a kind of a self-contradictory circuit in the sense that we said this, that the defining property of battery is it provides a voltage difference. As in, if you look at points A and B, you look at point A and point B, one thing you can say about these 2 points is that their voltage is different by this much, and that's because this is a battery. What's one property of wire that you also use when you're solving circuits? Someone from maybe this side of the class. It's a conductor, so so that's what it's made out of. But when you're trying to analyze a circuit using Kirchhoff's rules, what's the one property about the wire that you need to use over and over to analyze a circuit? Voltage is constant throughout the whole wire. In other words, if you take, let's say these 2 points, points C and D, I know the voltage difference between these two is equal to 0 because it's connected by wire. So that's where this contradiction comes up. What is the voltage difference between A and B? One part of the circuit says that this should be their voltage difference. The other part of the circuit that I have drawn says what? Yeah, because they're all connected just by wire. Well, something's gotta be wrong here. Now, I say this is contradiction, but it's not as though you cannot build the circuit. You can actually build it. You can actually, short a battery. I mean, I keep telling you not to do it, but nothing actually stops you from doing it. So, what do you think will happen when you actually build this circuit? Will the voltage difference between A and B closer to non-zero, maybe closer to this, or will it be closer to 0? Closer to 0? Yeah, let me try that in the simulation. So it's a question of, this is a reasonable simulation. I can build reasonable circuits here, as in I can hook up a light bulb and it'll light it up. It's possible that I might have to, wait.
I think you're using resistors.
Oh, yes, yeah, sorry. That's why I couldn't extend it. It just looked like wires. Okay, so I could hook this up to a light bulb, but it's probably not going to be quite bright. Yeah, let me do it with the 2 batteries so that it'll be brighter. All right, so if I hook it up to this, then it lights up the light bulb. And so here what I'm asking is, or what I'm going to now try to do is, so you can maybe take it for given that if this light bulb lights up, it would be because, wait, can I? Oh, wait, I do have a voltmeter, all right. So I can actually use voltmeter here. So let's see, this is the positive end, negative end, all right. Wait, sorry, the other way around. So that's the voltage. So when I connect it to the light bulb, then I still get the same voltage. So, so this is what would happen in a real circuit. So once again, I'm doing it in simulation, not with a real circuit, because for safety issues. But in a real circuit, if I connect these 2 wires, oops, can I? All right. If I connect these 2 wires together, then this is what you would get. In fact, I think this is making it, sorry, I should have tried it before class. So one thing that's realistic here is how the batteries are burning, because that's what you would see in a real circuit. And as the battery burns, you wouldn't expect to measure 14.4 volts here. It should have actually been something closer to 0 volt, because as the current flows, so what I want to do now is I want to, so this, how we are modeling things here, it's the model that's wrong. I have to modify something here to make this model more correct. And actually here's one thing I can do that I won't do this time because that's not what I'm trying to demonstrate. But you guys saw when we introduce circuits, the resistance of a wire, right? So instead of, so I could actually modify my model this way. So I could modify my model so that wherever I'm drawing a wire, it's not actually a zero resistance wire. It's actually a wire with some amount of resistance. Like I could express things that way. That would be one way to correct this model, as in here with this circuit, I could have done the thing that I did mistakenly. I can actually imagine that the wire that I'm connecting to this light bulb with, it actually has some resistance. So it's in series with some resistor. So it lights up the light bulb, and these resistors actually slow things down a little. I can model things that way. With that model, everything would be correct, or you wouldn't have any contradiction with anything. Because when I quote unquote short this battery, then this resistance still makes things slow down. All the voltage drop happens over these resistors, and you would get, you wouldn't have this statement here, and everything will be consistent with how you would analyze the circuit. So that's one way to look at it, and that's how you saw it when we introduced the circuit. With the power supply, it was able to provide a large amount of current, like 1 ampere, with a small amount of voltage, right? I want to look at things other way. When you build the circuit in such a way that the resistances of the wires are negligible, then how we would analyze that. So instead of fixing my model of this physical situation by acknowledging that wires have resistance, I want to fix it the other way. I want to acknowledge that my battery may not be perfect. The battery, so this is what we call ideal battery. Ideal battery will enforce this voltage difference no matter what happens. And this is the contradiction that you come across if you are too rigid about that no matter what happens. Because any physical battery you have will have imperfections. It'll burn when connected that way. So how would you model the imperfections that any physical battery has to have? So that's the situation where the idea of internal resistance comes up. You will see that as you work through some of the homework questions. So let's say these points A and B, they represent actual terminals out of a real battery. B is the positive terminal, and A is the negative terminal. So when we try to model this realistically, instead of saying that inside the battery, it's an ideal battery, we acknowledge, all right, it's a real thing, it's not going to be ideal. Instead, what we model it as is it's an ideal battery in series with something that's non-ideal. So the part of the battery that's non-ideal is that it does not have zero resistance. It has some idea of some quantity of internal resistance. This is where the picture black box picture is useful, because this internal resistance, it's not something that you can take out of the battery and measure. This is just how we model the characteristics of the battery. So when you look at it here, let's say we are trying to get the maximum current possible out of this battery. So if you have this battery, and or this set of two batteries, and let's say you are trying to get maximum current out of it possible, how would you connect this battery so that you get maximum possible current? Like, let me show you an example of measuring some current. So I could connect this battery to a light bulb here to get some current out of it, like the way you did it in lab, right? And so this measures 1.8 ampere of current. How would I modify this circuit so that I draw more than 1.8 amperes out of this battery? The length. So here the wires are actually ideal wires. Actual length of wire doesn't matter, because it's a matter of how things are being modeled. So if I somehow make it so that I can connect it with a shorter wire, that won't actually change anything. because the length of the wire doesn't mean anything in this model. This still is 1.8. So not shorter wire, but how would you connect to this so that the amount of current is greater? You have actually seen one in the lab. Yeah, put more light bulbs in parallel. That's another way I can do it. So let me do it this way. Let's see. I'll have to. So I'm going to be sure to measure current coming straight out of the battery. So let me put it this way so that I can read it more easily. So I'm going to, hook up this wire and just one more light bulb. Put them in parallel, meaning I have a connection coming from here to here. So that's one. That'll give me 1.8 ampere again. And I have another connection coming from here to here. And when that's done, it'll draw double the current, 3.6 ampere. I want you to imagine extending this to the most extreme possible. What is the arrangement of the circuit that would draw the maximum possible current? So Kevin, when you connect more light bulbs in parallel, what's the effect of doing that? In terms of, let's say, resistance of the circuit. When you add more light bulbs in parallel, what does that do to the resistance? Lower. You could say that's why there's more current here, according to Ohm's law. Okay, what's the lowest resistance can be? 0, right? How would you build a circuit with a 0 resistance? Just with the wires, right? That circuit. So let me do that. So I would never do this in an actual physical circuit, but with this simulation, I can imagine, all right, the minimum amount of resistance possible, I would just connect it with the wires. So I can do it this way. And in the simulation, I think it has an unreasonable expectation for the battery. But when you actually connect to something this way, you can measure the current, and you can measure essentially what is the maximum current output of a particular battery. And this would be another way of stating the imperfection of this battery, because ideally it would have been infinite. There would be no maximum limit to how much current it can provide. The way we say with the normal force, there's no such thing as a maximum to the normal force. But in reality, there is. If I push down with enough force on this table, at some point I'll break the table instead of there being enough normal force. So with the battery, we can describe the imperfection of this battery either with the internal resistance or with some idea of the maximum current that the battery can provide. So how do you think these two are related? The maximum current that the battery can provide and the internal resistance that we use as a model for expressing the imperfection of the battery. How? They're related in a pretty simple way. It's not a trick question. So how are they related? Yeah, they're related through Ohm's law. So you could say that maximum current there. So this is the actual circuit where maximum possible current out of this battery would flow before it burns or explodes or whatever. And this maximum current is given by Ohm's law by V0. This is the what's sometimes called open circuit voltage. That's the voltage you would measure if you had an open circuit. The circuit is broken somewhere, so no current flowing. So this maximum current, let me write it down that way. Open circuit voltage of the battery divided by, divided by the internal resistance. Okay. So this is the idea behind internal resistance. It's some resistance that's internal, inherent to whatever device you are looking at. And it's a way of modeling this actual physical device. And when you have modeled the battery this way, the physical battery this way, then even for this circuit, you will see that, well, it has any self-contradiction. The thing that we say about battery, it no longer says that between the two physical terminals of the battery, this says to be the voltage. Instead, it says between one end, one of the terminals, and the other point, which is internal to the battery and we can never access it. The rule about the battery says that, well, this voltage difference is V naught. But before you actually get the measurable voltage here, there can be additional voltage drop if there's current flowing. Yeah, so that's internal resistance. Well, we spent more time on that than I intended. But so you will see that in some of the homeworks. But once you recognize this idea, then in terms of applying it, it's actually pretty simple. Once you write in the internal resistance, you just analyze the circuit as you would analyze any other circuit.